about electron configurations. And the different ways that you can represent an electron configuration. You have the energy level diagram that we did before. Okay, so that's one way to do it. Another way to do it is the orbital diagram. Also, sometimes it's called a box diagram. That's where you have the boxes and you have the arrows in the boxes. So I want you to know what that means when you see an orbital diagram. But most of the time what we're going to use is a subshell notation. For electron configuration. So that's where I'm going to pick up with here. And we did want to do silicon. So if we want to do the electron configuration of silicon using the subshell notation, we would start with 1s and there'd be 2. So it's 1s2, 2s2, 2p6, and we have 3s2, and finally we have 3p, and silicon altogether has 14 electrons, so there's 2 more p. So you have 1, 2, 3, 4, 6 is 10, and then 12 and 14. So that's the subshell notation for silicon. Any of these ways of representing the electron configuration requires that you know the order of energies of these different subshells. And the easiest way to do that is to use the periodic table to tell you what the order of the different levels are. So that's why I wanted to show both the, to bring up the periodic table in here in this picture. So before I do that though, I just want to also point out a little more here with this electron configuration. There's another way of notating this, which is even a shorter way of doing it, a more abbreviated way than even the subshell notation. And that's if we use the noble gas core notation. When you use the noble gas core notation, what you're doing is you're representing some of the electrons in this whole string by writing down the atomic symbol for the noble gas that would correspond to part of this. Okay, so for example, everything from here up to here would be the same number of electrons that you'd have in neon. Electrons as neon would have. So what you can do is represent that part of it by putting the atomic symbol for neon in brackets. So that's what I'm going to do here in this down here. So let's do it for silicon again. So instead of writing out all this, I'm just going to put atomic symbol for neon in brackets, and then I'm going to follow it with the rest of the stuff here. The 3s2 and the 3p2. So that saves you a little bit of writing. Really the only reason you do it is because it saves you writing, especially when you get further down in the periodic table, where you have a lot of things to represent in all these subshells. If you just use the noble gas that comes before that particular element, it saves you a lot of writing. Now, I want to also point out the fact that the electrons that are left over here, they're outside this noble gas core. In this particular case, they're known as valence electrons. Valence electrons are the highest energy electrons, the ones that are the furthest out from the nucleus. They're also the ones, generally the only ones that are involved in chemical reactions, in bonding. Okay, so these are called valence electrons. You have to know that word valence electrons. Valence electrons are always going to be the ones with the highest principal quantum number in your electron configuration. So if we go back to this picture here, you can see that these other electrons that are in these subshells have lower numbers, the 1 and the 2. Those are lower than the 3. 3 is the highest numbers that you have in this electron configuration. And those that have a 3 are the valence electrons. Here they're listed outside the noble gas core. So valence electrons are never going to be in the noble gas core. They'll always be outside. Sometimes there's other electrons also outside that are not considered valence electrons. It turns out that the valence electrons that are in an element for the main group elements, which are the first 2 columns and the last 6 columns, the valence electron number is the same as the column number for the main group. For example, silicon here, if you look at the periodic table, well, silicon has 4 valence electrons. Column number 4, 4A, is the same as the number of valence electrons for silicon. Now, also the periodic table, besides telling you how many valence electrons there are, it can also allow you to figure out the order here that we have for any of these subshells. If you look here in this periodic table, you see that they have some of these columns shaded in blue, some shaded in yellow, some shaded in, I guess that's pink, and then the bottom ones here are sort of a greenish. Each of these colors represents this type of subshell that's being filled in when you get to the last electrons in that element. So if you see here, you can see that they're labeled with that. These are labeled as the S block because these elements that are in that color block represent the elements whose last electrons go into an S orbital. The next one over here is the P block. So this color for the P block elements, those are the ones over here. The S block are the ones in here. The D block are down here. And then finally, way down below, you have that F block. So how does this help us do an electron configuration? Well, I'm going to do that over here. Let's say, for example, that we're talking about nickel right here. And we want to do the electron configuration for nickel. Well, let's do that. Nickel. If you go all the way up here to the top where hydrogen is, you can see that you're in the S's. So this would be a 1s, and there's 2 blocks, although the second one isn't located right next to it. It's way over there on the right. But let's just imagine there's another block there. That would be your 1s2. And then you go down to the next row. See, the rows are numbered. The next row is row 2. And these 2 are also S's. So you have 2s2. And then you go over to the P's over here, and now you're at boron, but you're in the pink. So now you're in the P block. So now for every block here, every square that has an element in it, that's going to count as another electron in that block. So if you go all the way across there, you're in the 2p part of the periodic table, the 2p subshell. Once you get to the end, you've crossed through 6 different elements, so that would represent 6 electrons in that subshell. And then you come back here to row 3 and do the same thing. So these 2 would represent the S electrons, S subshell, 3s, and there's 2 there. And then you keep going. After that, you have the 3p, and there's 6 there. So we're just going row by row, then across here, then all the way across here. So we've done all this, done this. Now we're and the p. So we've done all this as well. Okay, so all those red arrows that I have here are represented now already in this part of the what we're talking about here, electron configurations. Okay, so now we'll go to the next row, and now we're right here, we're at row 4, and we're going to go here. Okay, so those would be 4s. So that's like again, there's 2 there, and now finally, finally to get to nickel, we go across here until we get to nickel right there, and then we stop. And that's if we count the number of squares there, number of blocks, that's 1, 2, 3, 4, 5, 6, 7, 8. So that would be 8 then when we're at that level. Now, the thing that you have to remember the periodic table is when you go down to the D's, when you go to the D's there on that yellow part, even though you're in row 4, right here, the D's are 1 number lower than the row number. So you do have to remember that little peculiarity there. So even though that's row 4 and we have the 4 S's right there, once we get to the D's here, now we have to drop down in our numbering. Okay, so right here is where we have to start with the number 3. So that next one is 3D. And we've counted over 8 blocks, so it's 3D8. Okay. So this is the whole electron configuration that I have over here on the right for nickel. I'm going to now write that in the subshell shorthand or subshell notation by noting that if we go all the way from here over to here, okay, so you look to the previous noble gas, this would be represented by argon there. And then you'd have the rest of it still outside that. So all these other electrons are outside the noble gas core. So we could instead, what I wrote there, we could say we have argon and 4s2 and then 3d8. That noble gas abbreviation right there. Now, if we look at this, even though we have actually 10 electrons outside the noble gas core, how many of those are valence electrons, do you think? Remember, the valence electrons has to be the highest number.
Just 2.
Yeah, there's only 2 valence electrons there. These 8 electrons aren't considered valence electrons. They are high in energy. They can take part in bonding, but they're technically not valence electrons. Okay,